Hi everyone! Welcome to a repeated measures example for DI models. In this video, I will be giving a walkthrough for the code from the example that can be found in the deep dive training section of the DI models website, and I will be running through it in my R window that you can see right here. So I've already installed and loaded my necessary packages, which are DImodelsMulti, DImodels, Reshape2, ggplot2, NLME, and contrast. So we're going to hop straight into looking at our data. For this example, we'll be using the SimRM dataset from the DImodelsMulti package, which we can retrieve using the data function specifying SimRM. And when we run this, we'll see a promise up in our environment, which we can click once to have print to our console. However, it's quite a big data set to be fit into such a small space, so I prefer to once again click it, which will run the view function in R and allow us to see it in our script area instead. As we can see, this data set has multiple different time points, specifically 1, 2, and 3, and a single response column Y. We also have 4 different species, P1, P2, P3, and P4, which vary in proportion across different plot numbers. And now that we're familiar with our data, we can move into the fun part, the modeling. We recommend users to start by comparing different variance-covariance structures using the simplest DI model that they will be fitting. In our case, this will be our ID model. As our data is longitudinal, we have 3 different options for our variance-covariance structure. The first of which is UN, which relates to the general or unstructured variance-covariance matrix and allows the correlations between our time points to vary from one another. The next is CS, or compound symmetry, which assumes that each pair of time points shares the same correlation. And finally, we have AR1, which relates to an autoregressive model of order 1 and assumes that time points that are further away from one another have a weaker correlation than those close together. So in our example, this would mean that time points 1 and 3 have a weaker correlation than time points 1 and 2 or time points 2 and 3, which actually have the same correlation as 1 and 2 and 3 are the same distance away from one another. To fit these models, we will do a call to the DImulti function from the DImodelsMulti package and fill out our parameters as follows. Our first parameter is Y, which asks for the column name or number that holds the response value. In our case, this is the column Y, or the column number 6. Next, as we're fitting a repeated measures DI model, we will want the parameter time, and this accepts a vector of size 2. The first entry for it wants to know the column name that holds the identifier for time points. In our case, this is the column called time. And then it asks for the structure that we are assuming underlies these time points, which for our first model, we are assuming is UN. Next, we need to know the unique identifier for our experimental or observational units. And we put this in through unit IDs. And in this case, that is the column plot. Next, we let it know which columns hold our species proportions, and that is the column numbers 2 through 5. Now we've referenced a lot of column numbers and names, and we need to let it know where to find that data through the parameter named as such, which is SimRM. Next, we let it know which DI model to fit, and as I said, this will be our simplest model, the ID structure. And finally, we let it know what method of estimation to use. We have 2 options here. The first being maximum likelihood estimation, and the next being restricted maximum likelihood, which will be ML or REML, or REML for short. In this case, we will be comparing these three models, but none of the fixed effects will vary between them, as we are only going to be changing the variance-covariance structure, which means REML should be our choice, as it will provide unbiased estimators for our variance parameters. If you were to fit a model using REML and compared it to another model which you did change the fixed effects for, you could not compare those two reliably. You would instead need to use the ML methodology. But we are now good to run this model and see it appear in our global environment. And our next two will have extremely similar calls to DImodelsMulti, so we'll just steal that code there and change our UN in our time parameter to a CS, and then to an AR1. Making sure to run both. And now that all three models are available in our environment, we can get to comparing. We recommend using information criteria to do these comparisons, specifically the corrected AIC, as we have quite a few parameters included, even in these so-called simple models. So how to find the corrected AIC of a model? We call AIC C, noting that the first C is uppercase and the second C is lowercase on each model. Making sure to change the name between each. And between these models, we will pick the model with the lowest AICC score, which in this case is our first model, or our unstructured variance-covariance matrix. And we will assume that this underlying variance-covariance structure is true for the rest of the analysis. Speaking of, it's time to jump into interactions. So we're going to begin by refitting our ID model using the chosen underlying variance-covariance structure of UN and changing our method of estimation from REML to ML, as we will now actually be comparing models with different fixed effects. Our next model call will be extremely similar to our first, so we will repeat that code, changing our model object name from ID model to AV model to reflect the next DI model that we will be fitting, and changing our DI model parameter from ID to AV. We are essentially going from our least complex DI model and building our way up to our most complex model step by step. As these models are hierarchical in nature and are also nested within one another, we can compare them using a likelihood ratio test. So we will do this by calling ANOVA, all lowercase in R, and specifying that we want to compare ID model and AV model. In this case, for our output, the most important thing to look at will be our p-value. Generally, we will choose an alpha level of 0.05. If our p-value is above this chosen alpha value, we will so-called fail to reject the null hypothesis that the additional terms in the AV model over the ID model are all equals to 0. But in this case, our p-value is below that alpha level, and therefore we reject this null hypothesis and assume that our AV model better fits our data than the ID model, or simply that the additional parameters are not all equals to 0 and therefore adds some value to the model along with the additional complexity. So we are essentially selecting the AV model over the ID model. And next we will move on to our next most complex structure, but before that, we actually want to look at the nonlinear parameter theta, which can be estimated at this step as we have now found an interaction. So we will snag our chosen interaction structure model, the AV model, change its name to reflect that it will now have the theta parameter included as an estimate, and include the new parameter estimate theta, which we will set equals to true. And once this has finished running, we can reference what its estimated theta value is using the $ theta. And it looks like it estimated theta to be around 0.955, which we can already tell is very close to the default value of theta is equals to 1. But we'll test if this additional complexity is worth it by looking at our AICC values. Well, it's not a test, it's more of a comparison, but we'll compare them and see which one is more worth it. So we once again take out our AICC of our AV model and compare it to the AICC of our AV model theta. And we can see that they're extremely close because our theta values are extremely close. However, our AV model is ever so slightly lower. In the real world, you could pick either of these models as they are so close in value, but in general, you'll want to pick the simpler model in this case, which will just be our AV model with no estimated theta term, or simply as theta is equals to 1. And now that we've tried out our theta values, we can move on with our changing interaction structures. So once again, copying our original AV model code, we will change to our next most complex model, which is the ADD model. So changing our DI model parameter to ADD instead of AV and running it. The AV model and the ADD model are nested, so we can use a likelihood ratio test to compare them. And we once again see that our p-value is below our threshold of 0.05. So we reject the null hypothesis and continue with the ADD model as our selected interaction structure. Now, instead of going up in the hierarchy, we are going to take a step aside for this video and look at the functional group model. While the simulated dataset was not simulated with any functional groupings in mind, so anything that we do here will be arbitrary, I thought it would be good to show. So for fitting the DI model that is equals to FG, we have to include this new parameter, FG, which will be of the same length as prop and in the same order as prop. So our first species proportion will relate to our first functional group, our second species will be our second group, etc. So in this case, I'm going to put species 1 into group 1, species 2 also into group 1, species 3 into group 2, and species 4 into group 2, and then run our model from here. As I said, the ADD model and the FG model are on the same level of hierarchy for DI models, so they are not nested within one another, which means we need to once again turn to our information criteria to compare them. And we can see here that our ADD model is better than our FG model. So we discard our FG model and continue with our ADD model. Finally, we will be looking at the full model, rather than our AV, which is fit using, once again, a very similar call to the others. And the ADD model and the full model are nested, so we can use our ANOVA call again. And this time, we see that our p-value is above our threshold of 0.05, so we fail to reject the null hypothesis that the additional parameters in full are equals to 0, which means we instead choose our ADD model over our full model. And we're finally done with looking at our interactions. At this stage, we would now test any additional structural fixed effects, such as treatments or weather effects, but the SimRM dataset includes no such columns, so this step will not be included here. Which means we're ready to just refit the final model. So we will take our ADD model call and modify it ever so slightly, calling it our final model. And instead of using our ML method, we're done with our comparisons, so we will have REML here instead. At this stage, we are now ready for interpretation. This can be done either by looking at the coefficients through printing the final model, looking at a bit of a significance value for each of them, or we can go a little bit more complex and look at the summary of our final model object, which just includes additional information. But we always find it easier to look at visualizations for the sake of interpretation. And there is an entire section on visualizations on the DIModels website, but I'm going to just do a simple one here for illustration purposes. Rather than looking at every community included in SimRM, or going the step further and looking at some communities that weren't included in that original experiment, I'm going to just look at a subset of SimRM, which I'm going to call SimRM_plot. And in this case, I am just going to look at the values of SimRM, which meet the criteria of having the plot number be in the set of 1, 3, 5, 7, or 21. And I chose this because plot number 1 is a monoculture of P1, plot number 3 is the P2 monoculture, 5 is the P3 monoculture, and 7 is the P4 monoculture, while plot 21 is an equiproportional mixture of all 4 species. In other words, they all appear at 0.25 as a proportion. As I'm going to be predicting from the model, I'm also going to exclude the column that has our response in it. So I'm going to take away column 6. We can now look at our SimRM plot and see that it does in fact include all of the predictive information, but not a response. From here, we can replace it then with our value from our prediction by calling the predict function on our final model using our SimRM plot values. Looking at this again, we can now see that we have retained our plot, we have our Y value estimated, and our time points. To make the plot easier to see, rather than just looking at plot numbers to remember what species are there, I'm just going to give them some names. So I'm going to create a new column called community, which is going to, each name is going to repeat 3 times, as we have time points 1, 2, and 3 for each community or plot. And then I am going to make them repeat each 3 times. Within here, I'm just going to give some names. So I'm going to paste together the letter P and the numbers 1 through 4 to be our 4 species monocultures, and then just the community mixture, which relates to our equiproportional mixture. Now we can see that our names have been added here. Now to just do a quick little plot, I'm going to use ggplot. Specifically, I'm going to use our SimRM_plot dataset and describe the aesthetics through AES, that function. The first of which is we are going to use a fill to separate our bars in our bar chart by time. We are then going to specify the y-axis to be our y value, which was our predicted y column. And then I'm going to use our x-axis as our community column, which is going to make it easier to identify what our actual predicted values were. And we're going to specify that I wanted a geom bar or a bar chart with position equals Dodge and stat equals identity, as this will give us a grouped bar chart like so. And we can see here that our mixtures appear to outperform any of our monocultures, which would be expected if our species interacted positively, which we saw that they did when we looked at our coefficients. A lot of our additive was positive, with one small negative interaction at time point 2 from species P3. Now we could leave our analysis here and be perfectly happy with our visualization. However, the main strength of DI models being in the repeated measures or multivariate sense is that we are able to formally test across our time points or across our ecosystem functions. This methodology is currently not in the DImodelsMulti package. It is a part of future works, so you never know, it might be there when you see this, but the website will have been updated. Instead, we can simply copy the call from our final model, which you can find at the very top of our summary. So that is this model function here. And these two are our correlation and our variance functions. So 0 to plot and 0 to time. Copying this, we can create our final model as a GLS function from the NLME package, where we include the model call that I copied from our summary, along with any of our additional information required, such as our data being equals to simRm. The method we used in the end was REML. Our correlation we took from our summary, which is of core sim relating to the unstructured in the form of 0 to plot, and our variance or our weights being equals to a var ident with 0 and time. The one thing about this, though, is our data simRm currently does not include any of our interaction structures because they were added within our package function call. So we are actually going to use the DI models package to create these ADD columns for us, and we will be able to create a new file called simRm_GLS, which we will update our data to reflect, which will have all of the columns that are included in our original simRm, and a call to DI data, which will build our interaction columns for us. Through this, we just have to supply our information from our original model, such as our proportions columns, which were 2 through 5, our data, which was simRm, our theta value, which was equals to 1, and what model we want, which was ADD. So now our simRm_GLS includes all of our original data set along with these interactions columns. But as you may have noticed, some of our column names don't quite align, so we will actually want to remove these underscore IDs from our model call. And we actually have a bracket missing here. So next, we just want to actually get this GLS model into the form that is expected by our contrast package. And this means that we need to change this interaction from a colon to an asterisk and select a species to drop from our monoculture estimates or our beta values. In this case, we'll choose P4, just arbitrarily. We'll also just specify this as form is equals to, and form is equals to. So now we should be ready to fit our final model GLS. And we should be able to then look at our printed out version to ensure that it looks how we expect it to. And in this case, we see we have our time 1, time 2, time 3 as intercepts with a P1, P2, P3, P1, P2, P3, and P4 as our interaction columns. Then they are crossed with time. This is why we had to drop a species, because otherwise we would have been overfitted, overparameterized. So now that we have our GLS object, we are able to formally test across our time points using what is called a contrast. And the function in R is called the same thing. We will first specify our model object, which is final model underscore GLS, and then we will provide it a list object for each of the communities that we want to compare. The first one, and only example that I'll give in this video, will be that we will set the time equals to 3, so the furthest time point that we have. We will set P1 is equals to 1, so that will be a monoculture, which means P2 will be equals to 0, P3 will be equals to 0, and then we don't need P4 because it's not included in our model. It's there implicitly, thanks to our simplex space. We then specify that our additive interactions will be 0, P2 add would also be 0. This is a monoculture, so we won't have any interactions included in here. And then our P4 interaction would also be 0. For our second list then, it will have the same appearance, but we will change one crucial thing about it. So rather than looking at a monoculture of P1, which we can see in our plot right here, we'll instead look at a monoculture of our P4. And it looks like at time point 3, these are vastly different, with P4 far outperforming P1. And how to get a monoculture of P4 here when it's not included here, we actually just set all 3 of our remaining species to 0, and that will implicitly have our species P4 be equals to 1. Once again, this is a monoculture, so none of these will be a value other than 0, as there's no second species to interact with. And then we will run this contrast test. As our p-value is below our general value of 0.05, we can conclude that our 2 different communities that we supplied at the same time point were in fact significantly different, with P4 outperforming P1 at time point 3. We could actually repeat this, and instead of looking at 2 different communities, we can look at the same community, so a monoculture of P1, and instead compare time points 1 and 2, because they look like they're performing very similarly. So if we look at time point 1 and time point 2 for the same community and run that contrast, we can see that our p-value is above our threshold of 0.05, and so we conclude that these 2 time points do not significantly differ from one another. And that's how easy it is to do a contrast once you're able to figure out how to fit this model in GLS, which you can easily just copy from the summary of your DIMulti object. I hope that this has been a useful video for you. Thank you for sticking around and listening.